Okay, can you hear me? Okay, so let me start. So last time we started studying homology, and yeah, we introduced the notion of n simplex. And, for n equals 0, it was 1 point space. For n equals 1, it's an interval. When equals 2, it's a triangle. 3, tetrahedron, and so on. And they can be, we can kind of realize them as a subspaces, some subspaces inside Euclidean. Inside Euclidean spaces, and we agreed that we will usually denote the vertices by V's. Always, so if you kind of pick some notation for the vertices, then we can usually note a simplex by sequence of its vertices, and in general we want to keep the order. So the order will be important for us, and then we also showed that for each simplex one can consider some simplices where we throw away some of the vertices, and we finished by introducing a notion of what we call delta complex structure on a topological space X, and there was it was defined as a collection of maps from such that each map acts from a simplex for some n, depending on alpha, to our topological space X, and they satisfy a bunch of conditions. I'm not going to repeat them in detail. Basically, there was a first condition that it's kind of one-to-one on interiors of the simplices. So for each, if you restrict on interior each of these maps, it will be injective, and moreover, for each point of X, there is unique alpha, so that this point so this point is obtained as an image of some point in the simplex in its interior. And the second condition can be summarized as kind of closed. This family is closed under restrictions on faces of the simplices. Face is an n-1 simplex inside an n simplex. So if we restrict this map on its face, we get another map from this family. And the third condition was about consistency of topology on X and topology on our simplices. So let me give some example. So consider X to be a 2 torus. As you by now should be very well familiar, torus can be understood as a quotient of a rectangle where we identify opposite edges. And this means we can introduce, again, in general, this delta complex structure can be essentially understood as some sort of choice of triangulation. So here we can triangulate like this. And let me denote the images of our maps. So there will be of our map sigma. So there will be, in total, let me consider, well, let sigma 1, sigma 2 will be a map from 2 simplex to X, and so that this will be the image of sigma 1, and this will be the image of sigma 2, and let sigma 3 and 4 will be a pair of maps from 1 simplex to X, so that this H will be an image of sigma 3, so this is just an interval. Of course, we know that it should be identified with this H. So this is also the same. This is the image of sigma 3. And sigma 4, actually I will need 5, I will need 3, sigma 3, 4, and 5. So let's, okay, let me actually do a different choice. This is sigma 4. This will be image of sigma 3, which is the same as this H, sigma 3, and this H, sorry, this interval diagonal will be an image of sigma 5, and we will need, finally we will need sigma 6, a map from a 0 simplex, which is a 1-point space, to X, and its image will be just this point, which is the same point, 6. So you see, if I, for any point, for example, if I take a point inside of this triangle, there is a unique, indeed, it satisfies all the conditions. So indeed, there is a unique sigma, which is here sigma 2, which so that it's an image of some point in the interior. You can also see that for each of these map sigmas, they are one-to-one on interiors. They're not one-to-one or outside of interior necessarily, for example, because this point belongs both to the image of sigma 1 and sigma 2, but it's not in the interior of the, it doesn't come from the interior of the corresponding two simplices. But it is, but it is an image of a point in the interior of a 1 simplex, which is mapped to this diagonal under sigma 5. And the second, you can also see that the second condition is also satisfied. So in particular, if I, for example, consider sigma 2, and for example, if I label these, order these vertices as follows, 0, 1, and 2 in this simplex here, then sigma 2 restricted on the face V0, V2 is equal to sigma 5. And these are considered as a map. So this is considered as a map from delta 2 to X, and sigma 5 is a map from delta 1. And here in this picture, I just show the images. Okay, so I hope this example is clear. Now we want to consider the following. For a topological space X with a given delta complex structure, let us define the following. So let's define delta n of x to be an abelian group. And formally write like this, meaning that this is a abelian group. Group generated by our maps in our family, which defines delta complex structure. So meaning what this means that an arbitrary element here is can be considered as a formal linear combination n alpha sigma alpha with the coefficients being integers. And so elements here are these formal linear combinations. So essentially for each of these maps, I assign a certain integer weight. And of course, just by my abelian group structure is given by just taking this by linearity. So if I take the sum of two such formal linear combinations, I just add up the corresponding coefficients. So here, one should note, so as I mentioned, that when we consider these maps, we usually want to keep kind of a fixed order of the vertices in our simplex. And but in principle, we can change. So in this abelian group, we can change the order of vertices by the possibly cost of sign, extra sign, change of sign of this sigma. Namely, one has the following dependence on kind of orientation of the simplex, or equivalently the order of our vertices. So suppose I can consider this sigma alpha defined on for a simplex with a certain order of vertices. So I can say this is equivalent, should be identified with minus sigma alpha, essentially the same map, but consider it as a map from a simplex where the vertices, the order is exchanged so that just two of them are transposed, two vertices are transposed. So if I transpose two vertices in my sequence, then this will change the sign. In this sign, meaning this is kind of -1. Formal linear combination. This has not, this of course has nothing to do with this. This is not some -1 operation on X, just minus operation in this abelian group. Okay. So we have this abelian group. And then we can consider what is called boundary homomorphism. Denoted by delta dn. And this will be a homomorphism from, denoted this, maybe, it's better actually. Let me denote this index as a lower index. So n, here n is some fixed integer which we take here. So here n is fixed. We only consider, for this delta n of x, we only consider our maps from simplices of fixed dimension. And then this, the boundary homomorphism will be a map from delta n of x to delta n minus 1 of x. And it's defined as follows. So we can, so since delta n is defined as a abelian group freely generated by this map sigma alpha, it's enough to define it on each generator. It's enough to say where sigma alpha is sent, where sigma alpha is a map from n simplex to x in our family, which defines delta complex structure. And this is mapped to the following linear combination of sigmas in this group. So we take a sum over I from 0 to n with weight minus 1 to the I. So this is just plus or minus 1. And I consider sigma alpha restricted to a subsimplex of delta n. So suppose this was defined on delta n, where we label vertices from v0 to vn. Then here we take a restriction to this subsimplex, which is a face of this delta n, obtained by removing is vertex. So I remind you that this notation means that this vi is omitted. So there will be n vertices. So this will be a map. This thing, this restriction, will be a map from delta n minus 1, n minus 1 simplex to x. So this indeed gives me an element in this abelian group. Any questions about these definitions? Now we can show the following property of this boundary homomorphism, which is crucial in defining homology groups, as we will see. So the proposition is that the following composition is 0. Well, this is understood, the composition is understood as a map from delta n of x to delta n minus 2 of x. This is because if we first act by the n, this takes us to delta n minus 1 of x, and then we act by the n minus 1, which takes us here. So again, to show this, it's enough to consider it, to show this on an arbitrary generator. So let's take us some sigma alpha, which is a map from n simplex to x, and just apply first dn using the definition. So this will be the following. And let's keep this outside, the next d. So okay, here just rewrite the definition, the sum of from I0 to n minus 1 to the I, sigma alpha restricted to a face where we remove vertex number I. Then I want to apply this again, dn. So how does this d act? Again, we want to remove vertices, we do this and do the sum with plus minus 1, determined by the position of the vertex we remove. So suppose so we can write it like this. Okay, we can actually take, so this is of course homomorphisms on abelian groups. So we can take away, we can use linearity, we can take this sum over I outside. And then we will act by this dn minus 1 on this sigma alpha restricted to this phase. And this will give us, by definition of boundary homomorphism, another sum. And okay, in the sum we have to, the sum essentially will be over vertices, which we remove here. So let's, and it will split into two parts. The first part where we remove one of the vertices here, and the second part where we remove one of the vertices here. So the first part will look like this. So the sum will be from j equals 0 to I minus 1. So we go up to till this place. And here we'll have sigma alpha, where we remove v0, vj, and vi. Sorry, we remove vj and vi, and j comes before I. And the second part, where we remove one of the vertices here, and this will be a sum from j I plus 1, the next vertex, to n. And it will be weighted by j minus 1. This is because we skipped, we already removed this vertex, so the sign will be not j, but since we skipped 1, it will be j minus 1. And then sigma alpha restricted to subsimplex, where we remove first vi and then vj. Okay, let me continue here. But now you see this is essentially the same. So if now I consider, okay, let me rewrite it in this way. So let's combine this and this first sum with the first half, and I just write it as a double sum. So here in this first part, j is before I, so I can write this as a double sum over I greater than j. And this will come with a sign. Total sign will be minus 1 to I plus j, combine together, and there will be sigma alpha restricted to the subsimplex, where I remove again first vj and then vi. And now I'll take this term and again I combine it, everything into a double sum. This will be a sum where j is greater than I. And the total sign is I plus j minus 1. And here sigma alpha is restricted subsimplex where I first remove Vi and then I remove Vj. And now, well, now you can actually, if you look at this, you can see that this is just two opposite terms. Right? If I just relabel here J and I, it will be just the same thing, except there will be extra -1 here, right? Because this -1 here, I can erase it and put minus here. And now these two terms, they just differ by relabeling I and J. So the result is 0. Any questions? This kind of setting is actually quite general. So one can consider the following general to fit it in kind of bigger picture. One can consider the following general definition. Sequence of abelian groups Cn and homomorphisms Dn, so that the Dn takes elements of Cn to elements of Cn minus 1, such that the composition of Dn with Dn minus 1 is 0 is called a chain complex. So it's often useful to denote this sequence using this kind of a long diagram like this. This is map delta n, and then we have a delta dn minus 1, n minus 2, and so on. Here it can be 1, and so on. Sequence of abelian groups labeled by integers. So usually it's assumed that it terminates for at 0, at the index 0, but in principle this is not necessary. But in all our cases, we consider that it will terminate at the index 0, and so it will stop C0, but formally the last map is just 0. And okay, so what is why this is something nice? Okay, so from this property, if you have this property, this can be equivalently understood as follows. So the fact that this composition is 0 is equivalent to the statement that the image of dn plus 1 is inside the kernel of dn. And this allows us to define what is called homology group, namely the abelian groups H, let me write it here, H, N, C. So C is this our chain complex. Sometimes, so again, chain complex, it's a collection, it's a sequence of abelian groups labeled by integers, and so it's usually denoted by just, I mean, the whole, this sequence is itself, the whole sequence is usually denoted by just C, or it can also be denoted by kind of C star, meaning this star can be replaced by any integer, or it's sometimes it's denoted by C dot. So there are kind of different notations. Use. So this Hn of C, which are defined as a quotient of the kernel of Dn divided by the image of Dn, Dn plus 1. So this is okay to do because the image is a subgroup in the kernel. And such abelian groups are called homology groups of the chain complex C. This is quite general, and so as we just saw, these groups delta n of x, which we defined using the delta complex structure of the topological space X, they provide an example of a chain complex. So in the case when our CNs are delta n of x, and Dn is the boundary, homomorphism as we defined it, then the corresponding homology groups of such chain complex, one can denote them by H delta of x. So they will depend on the choice of topological space X, and in principle they also depend on the choice of the delta complex structure on X. And this is called Simplices homology of X. Let us consider how this group looks in this example we have here. We'll just calculate them by definition, essentially. Okay, so first, to use this, we need to calculate, we need to determine what are these abelian groups delta n here. In our case, when x is a torus with this choice of triangulation, which determines us the delta complex structure. So, okay, we have only maps from 0 simplices, 1 simplices, and 2 simplices. In particular, the group delta 0 of x in this case is just generated by a single element sigma 6. It has isomorphic to z, which is one generator. The group delta 1 of x is generated by sigma 3, sigma 4, and sigma 5. So it's isomorphic to z3, the cube. And delta 2 is generated by a sigma 1 and sigma 2. And so it's isomorphic to z2. So here, yeah, in these, now from now on, we will always deal with the abelian groups. So this notation which I use, this triangle bracket, now will mean generated by an element inside as an abelian group. Because before we use this kind of the same notation to denote a group generated just as a group, not as an abelian group. Because here, I mean, we automatically, in other words, we automatically include the relations that they all commute. Okay, so this is our groups in our chain complex. So what about so now we want to determine the corresponding boundary homomorphisms, D0 and D1. Sorry, D2, D1, D2. And D0 is, by definition, you can, goes to 0. Tautological, because there is kind of, if you remove, there is just one vertex. If you remove this, you get nothing. So you just, well, this can be understood as just a definition of D0. Okay, so let's consider first D2. So again, we just need to determine it on our generators. So D2 of sigma 1. So what is this? Okay, so to here we need to be careful, and we need to again we need to fix an order of vertices. So suppose we fix for this triangle we fix an order like this, and for this triangle we fix the order like this. And then, well, this will automatically fix an order for one simplicity for everything else. So this will fix an order for this one simplex here, and one simplex here, and also one simplex here. So if you calculate sigma 1, okay, let's consider this by definition first. Then the others will be quicker. So okay, sigma 1, this, if we fix the order like this, so this is defined on a simplex, well, I will denote it just V0, V1, V2. So by definition, okay, so I have to do this sum of the restrictions of this map. So this is a map to our X. And in the sum, I remove four vertices here one by one. So I start by removing this V0. So the first term has sign +1. So I remove V0, and the rest is V1, V2. The second term will be with minus sign, where I remove V1. Be sigma 1 restricted to V0, V2. And the third, finally, I remove the last guy. And now the sign is plus. So, and here I have V1, V2. But now I have to express this. So since this is a maps from one simplex to each of these guys is a map from one simplex to X, I can express them using sigma 3, sigma 4, and sigma 5. And suppose I define them using order as in this picture, then, so okay, sigma 1 restricted to V1, V2 will be just sigma 3. Sigma 1 restricted to V0, V1 will be sigma 4. And finally, sigma 1 restricted to, sorry, that's not true. Sorry, sigma 1 restricted to V0, V2 was sigma 5, actually. And then the last term is sigma 1 restricted to, okay, nobody, yeah, I did this. Let me, yeah, this was, okay, this part was. Okay, nobody corrected me. Yeah, the last term using definition should be V0, V1. So the last term we remove with the last vertex. The last term is restriction to V0, V1. And this is sigma 4. Okay. Similarly, we can calculate D2 of sigma 2, another generator. And you can see that this is sigma 2, just completely analogous. This will be sigma 4 minus sigma 5 plus sigma 3. And you can see that this actually is the same. D2 acts on sigma, the image of sigma 1 under D2 and sigma 2 under are the same. Okay, now what about D1? Now we have to act on this by D1 on each of these three generators. D1 on sigma 3. Again, so there will be two vertices. Sorry, there will be two terms. First, I remove this vertex here, and I get sigma 6, this plus sign, and then I remove this vertex here, and I get this, which is also sigma 6, but with minus sign. This is 0. Similarly, for sigma 4, I get this minus this. This is also 0. Write explicitly sigma 6 minus sigma 6, 0, and D1 on sigma 5 is again sigma 6 minus sigma 6, which is 0. And of course, by definition, D0 on sigma 6 is 0. Okay, we know all these maps D's here, and so we are ready to calculate our simplicial homology by definition. So let's start, for example, H2 delta of our X, which is a 2 torus. Okay, so this is by definition, it's a kernel of 2 divided by the image. Sorry, H2 well, in principle, you can consider image of D3, but well, D3 is nothing, right? There's nothing in there's no 3 simplices, so it just it's empty. So this empty subgroup. So you just need to consider kernel of D2, and you see that the kernel will be generated by the difference between sigma 1 and sigma 2. So each individual of these guys is not in kernel, but the difference is in kernel, generated by the difference. And this is isomorphic to that. Now H1. So here this will be a kernel of D1 divided by image of D2. So what is a kernel of D1? Well, kernel is all of them are in kernel. So the kernel is generated by all 3 of them: sigma 3, sigma 5, sigma 4. So what about the image? Well, in the image, we have this particular combination, right? It's the same in the image of D2 of sigma 1 and D2 of sigma 2. So the image is generated by this particular combination. Sigma 3 minus sigma 5, 4. So there is essentially 3 generators and 1 relation. So this is the result. 2. And finally, well, this is the easy thing, H2, sorry, H0, delta of T2 is kernel of D0 divided by the image of D1. So the kernel of D0 is, so D0 itself is trivial, so kernel is generated by sigma 6, and there is nothing in the image of D1 because here is everything is 0. So this is it will be just generated by sigma 6. So this is isomorphic to that. So we found that there are 3 non-trivial homology groups. H0 is Z, H1 is Z squared, and H2 is Z. Final result, you can summarize. And as an exercise, I will leave it to you to do the similar calculation when X is a real projective two-dimensional space. And in this, for example, so we know that RP2 is similar to the torus. It can be given as a quotient of a torus, where we identify, sorry, not a torus, quotient of the rectangle, where we identify the opposite edges, but with reverse orientation. So this edge is identified with this edge, but reversed, and these two edges are also identified reversed. So, and we can also use the same kind of similar, not, of course not the same, but similar triangulation to fix the delta complex structure. In this case, one can show the homology groups will be Z for n equals 0. So n here in homology group is often called degree. So this Z in degree 0 and Z mod 2Z in degree 1 and 0 otherwise for all other n's. Exercise for you. Any questions at this point? I'm going to make the following remark that this, so the way we define this, we defined what we called simplicial, simplicial homology for the topological space X. In a sense, this is a bad definition. Particularly, why it's bad? Because it's, well, of course, it requires a choice of additional structure. Topological space. In principle, one can actually show that if one chooses a different delta complex structure, the resulting group will be isomorphic. But this is not what we want to do, and this is not usually what is done. So in particular, if one kind of tries to go this way, one will encounter that it's actually hard to prove theorems about homology groups. But in a sense, well, there is one kind of a plus of this definition which we consider it is that it's easy to calculate. Once we choose the delta complex structure, the problem of calculation is essentially some combinatorial problem. Because as you can see in this example of a torus. So this is not the homology is usually so we want to kind of define different homology groups, and but still using the same setting of chain complexes that we had. So we just essentially define a different chain complex, which is called singular chain complex. So X, as usual, is our topological space. For any topological space, one can define what is called singular complex. In general, chain complex is a sequence of abelian groups labeled by integers. In this case, this abelian group for an integer n is defined as an abelian group generated as a free abelian group generated by all continuous maps sigma from n simplex to x. There's no restrictions. We take any as a generators, we take any map, all possible maps from delta into x. So here there is no notion of no choice of delta of this delta complex structure here. So there is no fixed family of maps satisfying this additional property. Of course, this is in general space X. This is kind of there are infinitely many and uncountably many such maps in general. So this is a very crazy group. But what will happen is that the corresponding homologies are still usually quite manageable and nice situations, like when X is a manifold, the homology groups are finitely generated. So an arbitrary element here is written as a formal linear combination. Well, with finite number of terms, where each term here is understood as a map from delta n to x, the coefficient integer. Okay, so this is of course when we talk about chain complex, we need to consider boundary homomorphism. We want to consider dn, which acts the homomorphism acts from Cn to -1, and we will essentially define it similarly as a boundary homomorphism for simplicial chain complex. So here it's enough to consider again it's an arbitrary generator, which is a map from n simplex to x, and this map is sent to the following formal linear combination maps, and the formula is essentially the same as we had before. So again, if this is if you choose label vertices here by v0 dot 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 vn, you take a map of sigma, a sum of these copies of sigma restricted to subsimplex, where we remove is vertex. So this is understood now as a map from delta n minus 1. And one can, so the proof that this composition of dn minus 1 in dn is 0 is the same. Literally, I just follow the same argument. Main difference here, there was a kind of a predetermined nice family of maps for X, satisfying some nice properties, but here you just consider arbitrary all possible maps. And then again called boundary homomorphism. Because it's related to restriction of this map to the boundaries of the simplex. And then, so using this singular chain complex, we define what is called singular homology groups of our topological space X, which will be denoted by just a chain of X. And okay, this is by definition just a chain of this chain complex, which we just defined, singular chain complex, which again, just by definition, is a quotient of dn by the image of dn plus 1. So when people talk about homology of a topological homology group, topological space X, by default, they usually mean just the singular homology, which we consider here. Again, in principle, there are other versions of defining homology, but they all originate from kind of such choice of chain complex, but this is the most usual homology, singular homology. You can ask why it's called singular. Let me make a few comments on this. So I will make in general talk about some terminology which is usually used. Map sigma, single map from sigma from delta n to X is called this singular simplex in X. So here there is no condition on this map. So why is it singular? This is because, okay, if you consider, for example, three simplex like this, which is tetrahedra, and you consider this map to some topological space X. Here there is no, unlike in these delta complex structures, there is no requirement that it's one-to-one on interior. So in particular, it can be kind of the image can be a very degenerated simplex. For example, everything can map just to like to an interval. The image or just even a single point. The image can be sort of understood as a degenerated or a singular simplex. Of course, in the general kind of, it can be one-to-one on interior, but it's not required. Like for this delta complex structure. Okay, and now so this is a single map like this, and then if you consider some arbitrary element, in this our group Cn of x. So here sometimes, in this definition of singular chain complex, sometimes we will write explicitly the choice of topological space, but sometimes we are not going to do this. If it's clear what topological space we have. So arbitrary beta, an element here, well, it has by definition, it's a formal linear combination of maps sigma alpha. Each of them is a map from n simplex to x, and this is called n chain, or in this particular case, singular n chain. Elements of these abelian groups which define our complex, chain complex in general are called chains or n chains if we want to emphasize some fixed degree. And now if we consider element of a chain complex such that the n acting on it gives 0, in this case beta is called n cycle. Meaning that it kind of has no boundary. And if beta is dn plus 1 of some gamma, in this case, beta is called n boundary. Terminology, and then we can, using this terminology, informally one can say that Hn, which is by definition is the kernel of dn divided by the image of d n plus 1. Informally one can say that this is a space of abelian group of n cycles, consider it modular n boundaries. Any questions? So now we have some working definition of these homology groups. Well, now our goal is to develop a theory to some machinery for calculating them and showing some of their properties, similarly as we did for fundamental group. And we start with the following relatively easy proposition. So suppose X is of this following form. So X is a disjoint union of X alphas, so that X alphas are path-connected components. Of X. So any topological space can be presented in this form as a disjoint union of path-connected components. And then we want to show that in this case, the nth homology group of X is given by a direct sum of the nth homology group of our path-connected components. Well, this will follow essentially from the definition. So consider arbitrary element in our, well, arbitrary singular and simplex. We map from delta n to X. And so we know that this delta n is, of course, path connected. Then it follows that the image of this delta n should be also path connected. And then it follows that the image of sigma belongs completely to one of these path connected components. Belongs to some X alpha to some alpha. And from this observation, it follows that our groups of singular chains, which are, by definition, there are some the groups of formal linear combinations of our singular simplices, which are maps from delta n to X. And so each of them, each of these guys has image in one particular path-connected component. So this can always be split. This sum can be always split with respect to this with respect to this path-connected component. So this group is can be canonically identified with a direct sum of groups of singular chains in each path-connected component, just by separating these the terms here with respect to the image where they belong. And moreover, well, if we consider boundary homomorphism restricted the subspace of singular chain with the image in one particular X alpha, this image will be in Cn minus 1 for the same X alpha, right? Because if by definition this delta n is given in terms of restricting our maps to some to the faces, and of course if the original map has image in some of the X alpha, all this restriction will also have image in the same X alpha. That's why we have this thing here. And And this is essentially tells us that this Hn of x, again, which is by definition the kernel of Dn divided by the image of Dn plus 1, is so since since all these Dn they don't mix up different components in this decomposition, this means that this, when you consider the quotient of the kernel with respect to image, it will also split respectively in the sum of this quotient of Dn, kernel of Dn restricted to Cn x alpha and divided by the image Dn plus 1 restricted Dn plus 1 x alpha, and this is direct sum of Hn of x alphas. And this is what we wanted to show. Any questions? Another proposition which we will show is that we assume that X is non-empty. Sure, there is no problems with that, and X is plus connected. Then we want to show that H0 of X, the homology group in the degree 0, is isomorphic to Z. So it has a single generator. How do we prove this? So let's consider the map which we'll call epsilon. So the map from the group of 0 chains to Z. And it will act as follows. So an arbitrary element here is a formal linear combination like this, where each sigma I is a map from delta 0 to X, and delta 0 is just a one-point space. And we want this sum to be mapped to just the sum of the coefficients. So how does this look? So we have a topological space X, and well, the 0 chain can be understood as just a bunch of points, because each the sigma I here is just maps from one point space to X, so they're completely determined by the image of this single point. It completely specified this maps completely specified by the image. So then this sigma 1, sigma 2, 3, sigma 4, and these numbers here in the linear combination can be understood as some sort of weights which you assign to each of these points. We're going to assign plus 2, minus 1, plus 3, minus 4, and so on. Consider points with weights, and this is under epsilon. In this particular case, under epsilon, this is mapped to, well, remember this is degenerate case, so it's like minus 5 here. This is mapped to minus 1. Just take the sum of all these weights for all points. Okay, so and this is definitely because X is not empty, this map is definitely surjective. given integer, just take one point with weight being this integer. And since this is surjective, then this means that the image of this map, which is the whole Z, is isomorphic to the quotient of C0 of x with respect to the kernel of this epsilon. But from the other hand, we know that by definition, H0 of x is a quotient of the kernel of D0 with respect to image of D1. But D0 it just acts trivially, so kernel of D0 is a whole C0 of x. So H0 is just a quotient of C0 of x with respect to image of D1. Therefore, to show that this is H0 of x is isomorphic to Z, it's just enough to show that the image of D1 is the same as kernel of epsilon. To show this, then we are done. So we need to check statement. And we'll do it as well, actually will often happen in the rest of our lecture course. We'll kind of show such equality between two different subgroups in abelian groups by showing inclusion in two different directions. So first, let's show that the image of D1 is contained inside of the kernel epsilon, and then we'll show the inclusion in the opposite direction. Okay. Well, it's enough to show that if we consider, so an arbitrary element in this image is D1 of some, okay, it's enough to consider its own generators. So we consider the action of D1 on some generator, which is the singular one simplex. And we want to show that this is in the kernel. So we know to show that if we then act on it by epsilon, we will get 0. Okay. So first, so this sigma is a map from delta 1 to x, and let's denote vertices here v0, v1. So d1 is a sigma restricted just v1. We remove first the v0, and then with minus sigma we remove v1. So yeah, we remove v1, so we get v0. And well, this is now these guys are singular 0 simplices, and they come with coefficients +1 here and -1 here. So by definition, epsilon takes the sum of these coefficients and gives us 0. Okay. So this is inclusion we checked. Now we want check the inclusion the other way. So let's take some element here in the kernel epsilon and show that it's also in the image of D1. So arbitrary element here is is of the form sum of mi sigma I, where each sigma I is a map from delta 0 to x. And since it's the kernel, the sum of these coefficients is 0. This means that I can rewrite it as follows. Let me take it like this. Sum of sigma I, ni minus ni sigma I minus sum of ni's, which is just 0, so I don't actually modify anything, times some sigma 0, and sigma 0 is the following. So let me take some fixed point x0 in x, and let's sigma 0, the image, we choose the sigma 0 such that its image is this one-point set. So sigma 0 is again some 0 simplex, completely determined by its image. But now we can rewrite this as follows. So this will be a sum of ni, sigma I minus sigma 0, sum over I. So if I look at this picture, which we had before, so we can introduce, we introduce some point x0 here, but since it's a path connected, right, for each of these points which I had before, I can choose a path from x0 to each of these points. And let me denote this path as tau I. Namely, if image of sigma I was a one-point space with point xi, let me take ti to be a path. So ti, a path in x, so namely it's a map from interval to x, so the ti of 0 is x0 and ti of 1 is x1, sorry, xi. But this interval I can consider as a one simplex, right? And then this sum, I can notice that this sum, each term here can be understood as a d1 acting on this ti if I consider it as a singular one simplex, because sigma I is a restriction of ti on 1, and sigma 0 is a restriction of ti on 0. And then this is d1 of sum of ni ti, and this is indeed in the image of d1. So we show the inclusion in the other way. So this is done, and therefore this is done, and therefore these are indeed isomorphic. Okay. Any questions? Okay, if there are no questions, that's it for today.